neutrons will start at 0, corresponds to 9 degrees in the laboratory system, and go forward. And all the heavier particles, you have to look at the forward direction, forward of the target. But we feel there's a lot of physics opportunities that one can study if you have an instrument like that. As I mentioned, single particle structure, mapping out the single particle strength, new closed shell, for example, G132. Then astrophysics, you want to study the nuclei of interest for the R, well, not so much S, but the R process, the RP process, using these reactions. You can study pair transfer, one neutron pair, one proton pair transfer, or one neutron transfer, sorry. Inelastic scattering, various surrogate reactions that simulate neutron capture in stars. Then I'll talk a little bit about how we actually implemented this at Argonne. So the big problem is getting a magnet. A magnet of that size, it has to have a big bore, it has to have a high field, and so it's basically a superconducting magnet, and they're kind of expensive. So we looked around, and it turns out that MRI machines have exactly the right magnet we want, pretty much. So we were looking around for MRI scanners, and we found one in Tübingen in Germany. That this is Raymond Argonne, who is graduated from the Technical University in Munich. And one of his colleagues there actually went to work for this Siemens company. I think you know about it. It's a very big company. They make a lot of MRI scanners. And he asked them, do you by any chance have an MRI scanner that you would like to give us? And the surprising answer was yes. We have one sitting in Tübingen that is running out of its lease. And they were willing to give it to us if you would pay for the transportation cost. So that's what we did. We went over there in November 6th, 2006 to see that it got dismantled. So this was Monday morning. It looked like this. A really nice MRI scanner. It looks beautiful, all this plastic and nice soothing colors. This is what it looked like 2 days later. The magnet was put out. You can still see where the patient would go in. There's still some coils inside and all that, but otherwise it's a big superconducting magnet. It's still filled with liquid helium though. You need to cool it down with liquid helium to make the coils superconducting. And the surprising thing to me was that you leave the helium in, it's cold, that's a 4 degree Kelvin or something like that. You take the whole thing, you put it on an airplane and fly it across the Atlantic with 2,000 liters of liquid helium inside. And they're used to do that. They have special contracts with airlines to do this. And they do it a lot. They do it several times a week. They deliver one from Germany to the US, get installed in hospitals and so on. So it arrived on December 8th, the coldest day of the year. We lifted it off the truck with a big crane, and here we see it just barely got into the garage door, into the experimental area. And this is the best way to show it, because otherwise you can just see the tank outside. So this is our implementation of it. This is an engineering rendering drawing of it. So again, we have the beam comes in here. We can mount targets on this target fan here. It can actually move forth and back depending on the experiment. And we can select different targets here we want to bombard. This is the silicon detector array. That was actually the responsibility of Alan Wasserman and his students here to put that together, and I'll show you a little bit more about it. It's a very nice, that's sort of the heart of the system, because that's what has to detect the particles. We also have here, in some experiments, we also have a recoil detector array here. So you detect not only the proton, for example, going backwards, but the recoil will go forward. And if you identify and measure that here, you can cut down the background other reactions that occur at the same time. So that is the way it was put together. And well, one of the first things we had to do is to measure the magnetic field inside. We need a relatively uniform magnetic field for this whole concept to work. So that actually was the project of students also from Western Michigan University who did a lot of work in mapping out the magnetic field with Hall probes rotating around and putting in many, many different positions inside. So this is the final map that came out. So you measure the longitudinal component of the field at right on the axis. That's an r equal to 0 here. And we're not going to call something that's this one here. And then you go out in 10 centimeters larger radii and measure it. And you see you develop these radius. But in the central 1 meter, plus minus 50 centimeters, it is quite uniform, even out all the way out to the bore of the magnet. And we also measure the radial component of the field, because there are radial components. Because there's some coils that run the other way around that try to clamp down on the what we call fringe fields, which otherwise extend very far. But again, you can see here that you have a nice uniform field here. So basically, we have a uniform field in this volume here, 90 centimeters diameter and 1 centimeter long. 90 centimeters is the bore of the magnet. So the particles going around in this area here will obey the nice kinematics that you expect. So we found a place in our former area that was called just the general purpose area, and it barely fit in, but it did. And this is sort of what it looked in July 2008. Still what it looks like. And the beamline coming in here with various quark poles to refocus the beam so we have a nice spot on the target. Now we have this long rod that the silicon detectors are put on, and we have to get it through that. So focusing is an important thing. Well, here we have the silicon detector array. So there's a hole in the middle that's 1 centimeter, and the whole thing is about, I think, 70 centimeters long. So you have to focus the beam through that. So that's an aluminum rod, basically. On the outside of that, we have a little anchor bracket here. On top of that anchor bracket is glued a piece of PC board with a lot of traces in it. On top of that, we glued the silicon detector wafers. So now we have a nice surface here with the silicon on it. And let's see. That's what it looks like. You see here the silicon, the whole array. It's on 4 sides. These are not the ideal silicon detectors. These were some we had available. We are in the process of buying some that are bigger, so we don't have these dead areas here. At the end, we have some slits to measure if the beam wears off course a little bit. And this is what looks sort of close up. This is a silicon wafer. You have to make contact with both ends of the silicon. So these are these little bonding wires that Scott Marley actually bonded on out at Michigan State University. You have to read them all. Let me back up because I didn't explain how this actually works. So the way you get the position is to measure the signal at both ends of the detector. On the front surface here is a resistive layer. So depending on where the detector, the particle hits, you get in this case, a larger signal on this side compared to that side. By having those two signals and measuring the total energy from the back side of the detector, you can actually calculate the position very nicely. And it gives you a position resolution of something like 1 millimeter out of the 5 centimeters that the detector is. So that was an important parameter, as I pointed out earlier. We need to know that. So then I'm just going to go through very briefly a couple of early results. So we did in August, when was that, 2008, I think, yes. We did the first experiment, which was a commission to see if does the concept really work? Can we get the resolution we think we can? Or are there other things that come into place? Well, I think we have simulated it correctly because this is what we got. You see these kinematical curves. Laboratory energy versus actual position. These are different states